In Chapter 8, we're going to talk about sampling methods, and the central limit theorem. Before we actually get to those, let's begin by talking about sampling error. Anytime we sample from a population, in order to estimate the parameter of the population from the statistics that are derived from the sample, there's bound to be error. And the error, that's the difference between the value of the population parameter and the value of the sample statistic that tends to estimate it, is called sampling error. So that's what that is. Sampling error could be positive, negative, or zero. Typically, we take the absolute value of sampling error, unless you want to be specific as to whether you under or overestimate it. So what I have here is I've made up just some simple examples. So for instance, let's say the parameter of the population is a mu, which is the subject of this chapter, the population mean, in other words, and we're going to approximate it or estimate it using the sample statistics x bar, the sample mean. So the error in this case is going to be the value of the parameter minus x bar, the statistic. So for instance, let's say the mean of the population is 100, and I'm choosing 3 different samples. Each sample results in a different sample mean, which is the likely case anytime we sample. So in each of these, in the first instance, I have a sample mean of 96. Second one 105, and the third sample mean was 100. In first case, we are underestimating the population mean by 4 units. The second, we are overestimating by 5. Actually, that's what that is. And finally, in the third example here, if the mean is 100, the sample mean also shows 100, therefore there is no error in this case. Now bear in mind, when we do this, when we actually go collect a sample, we do not have information about the population parameter. If we did, then there will be no need for sampling. True? So this assumes that we do not know the sample mean, and our work assumes that we don't know the sample mean and we would like to estimate it. Now, and by the way, what I have up here suggests that the sample mean itself, x bar, ends up being a random variable in our work. That means I don't know what the value of the next sample mean is going to be as an estimate of mu, and that the fact that it varies each time I choose a sample, even the same size, it makes x bar a random variable. Now, we talked about sampling error. Now let's talk about non-sampling error. The non-sampling error is pretty much any other kind of error that is not related to sampling. So these could be the clerical errors, the typos, put in an extra 0 in front of a number that ends with a 0, or just putting an extra digit, or just anything that may result in some kind of a data entry error or input errors. And generally with sampling, non-sampling errors, what they do is they introduce bias into our work. So again, these kind of errors are pretty much, they're not related to sampling, and a lot of times these are beyond our control. Now certain aspects of it, the clerical errors, we could have system of checks and balances and audits that can actually try to remove these kinds of errors. And once we get past that, we talk about sampling distribution. Now the sampling distribution, this is sampling distribution of a statistic. Maybe I should put that on there, sampling distribution of a statistic, because that's really what our focus is on our statistics. And remember, the statistic, when we talk about statistic here, we're not talking about the subject. We're talking about the numerical measures that are obtained from the sample. Those are called statistics. So the probability distribution, that's what the sampling distribution of a statistic is the probability distribution of that statistic when we take repeated samples of the same size from a population. Now, one thing that we are not mentioning is when we say repeated samples, right in here, repeated samples. Well, how many times do you repeat it? The theory says infinitely many times. That's what the theory says. This is rather a theoretical concept. Now, so for instance, in chapter 8, we're talking about the sampling distribution of the sample mean x bar, because we want to estimate the population mean. So by that we mean the probability distribution of x bar. This would be our statistic up here. See, that's x bar. When you take a repeated sample of same size and from a population with some mean and some deviation. Okay. Now, why do we need to know the sampling distribution of x bar? Well, remember I mentioned earlier, sample mean ends up being a random variable. For any random variable, we need its probability distribution in order to make probability statements about it. We can define events for that random variable, and then we try to find probabilities of that event happening. So that's why we are about to do. We are about to make probability statements about the sample mean now, not an individual observation, but a group of observations. So in order to answer those probability statements, we need to know the sampling distribution of x bar, or any statistic for that matter. Later on, this would be our next week, our next lecture, we're going to talk about confidence intervals and hypothesis tests about the sample mean. So that's another instance, or those are other two situations where we need to know the probability distribution of x bar. Okay, so hopefully that explains why we need to be doing this. Now, and that's kind of what I mentioned here. So if we know the sampling distribution of the sample mean, or the probability distribution of it, then we can make probability statements about it. And here I just made up an example. Suppose in a classroom there are a bunch of students sitting there, let's say 30, 40, 60, 15, whatever, however many the class size is. And we want to know what is the probability, the average age of the students that are sitting in that classroom lies between 23 and 26 years of age. Notice we are not making a statement about a single student. I'm not saying what is probability. I randomly select one student and he or she is 25 years old or between 23 and 26. We're talking about a group of students, not a single student. And that's what we're going to be looking at later. So we have one theorem in this course, and this is it. The central limit theorem, this is in your book. The central limit theorem pretty much lays out the shape and the parameters of the distribution for us. Okay, so here's what central limit theorem tells us, and this has to do with the sample mean, sampling distribution of x bar. So the central limit theorem says if all samples of a particular size are selected. Now, how can you select all samples? A lot of times there are infinitely many. Again, this is a theoretical concept, so that means a lot of samples of a particular size are selected from any population. Notice, not normal, from any population. The sampling distribution of the sample mean is approximately normal, and it improves, the approximation improves with large samples. Now, large samples for central limit theorem is samples of size 30 or more. So we're going to consider that large. 30 or more. So there you go. It gives us again the shape of the distribution. It's normal, approximately normal. Now the parameters of the distribution, I have it for you in a moment. I'll show you. But here is an illustration of central limit theorem. So here, this is from your book. Let's say we have 4 populations that we are interested in, let's say, sampling from. The first one is a U-shaped population, second one is a triangular, third one is uniform, and the fourth one looks like some kind of an exponential decay population. Okay, the point being that these are your any population that central limit theorem references. None of these are normal. Okay. And by the way, the central limit theorem, the other version of central limit theorem also is out there that reads, if all samples of particular size are selected from, instead of any population, make that any into a normal population. From a normal population, the sampling distribution of the sample mean is, instead of approximately, now we have exactly a normal distribution. So if we sample from a normal population, the distribution of X bar will be normal also. And that's regardless of the sample size. It has nothing to do with large samples. Only for normal populations. Okay, so let's address this diagram. Now, what the authors do, they actually take now, let's say, repeated samples infinitely many times from each of these populations. Look at the first one. Does not look like a normal population. This one does not, but it's not too bad. It is left skewed. This one from uniform repeated sample of size 2, and the probability distribution of those is going to be triangular, and this one gives you a right skewed distribution. Okay. And I'll do an illustration of central limit theorem for you using another software in a few minutes also. And there you have it. Now, if we take repeated sample of size 6, 6, 6, 6 from each of these 4 populations, remember the shape of these. As I scroll down, we're going to lose these. Look at this. Only with sample of size 6, repeated sample of size 6, the distribution of X bar, notice these are X bar, X bar, X bar. The original population is X. There is a subtle change in the random variable. Up here, X, 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 X. Those are the random variables. And these are the means. This is the histogram of all possible samples of size 2 if you draw from that population. So that's why a random variable is now X bar. And look at that with sample of size 30. That's why 30 is the magic number for central limit theorem. Here is the sampling distribution. Almost normal. Almost every one of these are approximately normal and kind of skinny too, right? That means they have lower deviation than the original population's deviation. Okay. So now here what I've drawn is if you sample from a normal population with mean mu, deviation sigma, random variable x, the sampling distribution of X bar will also be normal. And what's interesting is that it's going to have exactly the same mean as this one up here. The deviation of this group of scores, random variable X bar, is going to be actually less than the deviation up here. And the reason is because the deviation for distribution of X bar is related to the deviation of the parent population of random variable X by means of this formula. You divide sigma over square root of n. This number will always be less than the one you started with up here because you're dividing by positive number, which is greater than 1, by the way. That's why. If it was less than 1, it would be different, but it's greater than 1 because your sample size is usually large, greater than 1. We cannot have fraction or decimals for samples. So anyway, sigma X bar will always be less than sigma X because of this formula. So here's how the two are related. The mean and the deviation. The mean of X bar would be exactly the same as the mean of the X, random variable X. The deviation of the random variable X bar would be the deviation of, again, the original population, that's sigma, random variable X. I just left X out here, divided by square root of n. And those are the parameters of the normal distribution that central limit theorem gives us. Now this quantity sigma X bar is called the standard error of the mean. Standard error of the mean. By that we mean the standard deviation of the sampling distribution of X bar. Okay, that. And I can show you an illustration of central limit theorem now using a different software. So I'm going to pause this and then come back with illustration of central limit theorem. Okay, so I'm here in StatCrunch, a different software that I use from time to time for my statistics classes. Okay, so let's actually take a look at, we're going to look at the demonstration of the sampling distribution here, okay? Now Megastat, by the way, cannot do this, or I would show it to you in Megastat. So here's what we want to do. Let's say this is a population we want to sample from. Let's actually try the right skew distribution, kind of like that that exponential decay that your textbook had. And there you go. So this is the population that we are actually sampling from. Okay, so notice how skewed, severely skewed, far from normality. Now we know the parameters of this population. The mean is what we're focusing on, and the standard deviation. Don't worry about the median. So for this made up example, the population, we know the mean is 14 and change, 1405, and the deviation is 11.8255. Now remember, in real life we don't typically know these numbers, but for now we do. So here's what I'm gonna do, just like the book did. I'm gonna take repeated sample of size 10 from this population. So this is sample of size 10, and I'm just gonna do it one time so you see how this is. So let's say I'm going out to the field now and drawing my numbers, and here they come. So you see how the software is now selecting individual scores from this population. So there you go. Here's like a dot plot of those 10 scores. The mean of these first sample of size 10, the mean is 15.4 and the deviation is 11.87. So look how close it is. The deviations are very close, and the means, however, they're off, right? So there is a quote-unquote sampling error that we talked in the beginning of the video. The sampling error, the difference between the parameter 14 and the statistic 15, let's say, and a half, there's almost 1.4 unit of sampling error. So what the software is doing, though, notice we're putting aside X bar. So this is like X bar 1. Let's do this one more time. So you can see now these selections are being made from the population. Now we have a second sample of size 10. This time the sample mean is 19.5. Look how individual results vary drastically. The mean was 19.5. Deviation is 14.7. Okay, now down here is what our focus is, folks. See, these are sample means. These are individual samples. Okay, so far we've sampled twice from this population. The average of the two sample means, that would be the mean of two means. Mean of two means is going to be 17.49. How is this calculated? Remember, the first number was 15.4. The second one was 19.5. If you average 19.5 and 15.5, the average to 17.5. Okay, roughly, I'm rounding those. And this is the standard deviation, by the way. The standard deviation so far of these two scores is 2.92. Now let's do this 5 times. So here's our first sample of size 10, and if you note in here, each mean, see, this time is 10. That mean is moved over here. Next time the mean is calculated to be 14. It's moved over here almost. So notice individual means, that's what I was saying, individual results vary. That's what makes X bar a random variable. So there you go. This would be the end of the 5th sample. So far we've taken 7 samples. So there's 7 sample means in here. The average, and there you go, number of samples 7. The average of these 7 means, the mean of 7 means is 14.6. Notice now how close that is to the number up here. 14 and a half, not bad. Our sampling error is only about half a unit. The standard deviation, you don't expect this this one 10.8 is an estimate of that one. That's fine. But this number, it's like, how come it's not 11.8 or close to it? Well, it's not gonna be. Central limit theorem says this number is going to be sigma over square root of n. In other words, if you take 11.8 divided by a square root of 10, 11.8, that's sigma over square root of sample size and 10, you're going to get something that's very close to 3.8. Okay, now let's do 1,000 times. We just did. Okay, it was too fast, you didn't even see it happening, right? The drop down only happens per sample for sample of size, just one time for sample of size 10. But look in here now. We already had this sample of we have done this 7 times. We did it 1,000 more times. Now we've done it 1,007 samples. Look at the mean, the average 1403. Look at the mean up here. You see how close they are? Very close. And the standard deviation, again, that number is 11.82 divided by a square root of 10. So far, it's going to be approximately 4. Okay, and then look at down here. Let's see that distribution is almost like the one that's in your textbook. It's a slightly skewed to the right, but it's approaching normality, isn't it? You see that? Now, let's do this 30,000 times. And as I do this, keep an eye on this green blob. This blob that I call it, the green, this is the sampling distribution of the sample means. So here it goes. And if you keep track of, by the way, here, the mean here, this mean is going to be a point estimate of this mean. The sigma that you see here is 11.8 divided by a square root of 10. That's what this number should be. So here it goes. 30,000 times. And 22, 27, 28, 29, 30,000 right in here. You see that? Look at that distribution. You see how nice, normal, almost normal distribution that is. Look at the estimate of the mean, 14.05. Look at the parameter, 14.05. There is hardly any sampling error now. True? Now look at this deviation is 3.75. I bet you if you take your calculators, you divide 11.8255 by 11.8255 by square root of n, square root of 10, you're going to get 3.75, something very close to it. You see that? So I can do this, forever. Now, this is what the central limit theorem says. If you take repeated samples, see, I'm just double clicking on the 1,000 times, and the shape is not changing at all. Look at the parameter. I've done this 87 times. Let's do 100,000 times. It won't take long. There, how I did. These are 100,000 repeated sample of size 10. Look at the shape of the distribution, practically normal. The mean is almost identical, and the deviation is what 11.8255 by square root of 10 should be, almost that. And note that we did not sample from a normal population. Still, the sampling distribution of X bar is normal. Now, let's change that. Let's sample from a bell-shaped distribution with a mean of 1,000. And oh, another thing, by the way, if I passed, I could go back, but that's okay. One thing I did, my samples were of size 10, weren't they? Repeated sample of size 10. Central limit theorem requires the sample size to be at least 30 when you sample from a non-normal population. So even with that violation of that rule, the approximation or the approach to normality was impressive. Now this time I'm sampling from a normal population with a mean of 1,000, and let me make the sample deviation, let's make that to be 10. That's too narrow. Let's make it to be 100. Okay, compute, and there you go. So we have our normal. This is the population that we are going to get our sample from. So the field that I'm going to, this is where the distribution in that field looks like. The mean is 1,000, deviation of 100. So let's take a sample of size 10 again from this population. I'm going to do it one time so you can see how the scores are selected from this population. And this is, by the way, sampling with replacement. That means the software has a potential to reselect, as you just saw. It can reselect from the same spot. So that's why, like you say, well, why do I want to sample with the replacement? And this is an example of sampling with replacement. Or actually, no, I'm sorry, this is without replacement, because once this one was selected, it was not put back into the pool. Sorry about that. So this was sampling without a replacement. Okay, but because there's so many observations at that point that they could be, the value could be reselected, but not the individual element could be reselected. So sampling is without replacement here. Okay, so I took a sample of size 10. And this is what happens in reality. You're only going to take one sample. So let's say I did my one sample. I'm going to come home and do my stuff. So in that one sample, my estimate is 1,001 of 1,000. That's not bad. With one sample of size 10, small at that. We like samples of 30 or more. So the estimate is 1,001. Not bad again. Off by 1. And deviation of 114, again not bad, versus 100. This is just with one sample with realistic case. And there's the mean 1,001 is logged right down here. That's x bar 1. Let's take 5 more samples. So again, just like before, each time the mean is going to change, deviation is going to change. See? And then it's going to be logged here or moved over here. Look at this one, 1,002. And down here is keeping track of the sample mean. See, with 3 samples, 4 samples, their average is now 988. 5 samples, the average is now 999 almost, or 998. It's approaching 1,000, isn't it? There you go. And once I took the 5th sample, total samples selected were 6 right in here. And there you go. That's the mean, which is very close to 1,000. What about deviation here? That's going to be 100 divided by square root of 10. Should be 25 and change. Okay. So let's do 1,000 times. With repeated samples, 1,006 is my running total of repeated samples of the same size, size 10. Look at this green blob again. It's almost normal. The mean of these 1,006 sample means, mean of means, is 1,001. Look how close to 1,000 that is. Its deviation is 32.3. Again, that's if you take 100 divided by square root of 10, it should be this number. My next example that I'm doing in a moment, I'm going to choose a sample size that I can do without calculator, and I tell you what this number should be. So anyway, and of course you can do this as many times as you like. Look how normal this distribution is with just 10,000 repeated samples, and look how close the mean is to the actual mean. So now I'm going to change this. I'm going to go sample size 25 to where I can take the square root of that easier. Okay, so what am I expecting? I'm expecting the mean down here to be close to 1,000. And if you divide 100 by a square root of sample size, the square root of 25 is 5. 100 divided by 5 is 20. I expect down here standard deviation of all the means in this histogram to be 25, right? That's 100 divided by square root of 25, which is 5. 100 by 5 is 20. Down here 20, up here 1,000. And here he goes. Let's just do one. Well, if I do one time, it won't drop anymore. For the software to drop, you see the selections, and must be 10. Anyway, boom, here's 1,000 times. So remember, our focus is down here. The mean 999.9, almost 1,000. Remember my deviation was 20. I was expecting 20. That's 100 over square root of 25. 20.6. Let's do 10,000 times. There you go. Look at the mean. 1,000. Look at the shape. Almost approximately, almost exactly normal. It's already approximately normal. And look at the deviation. Remember, I was expecting 20, and it is 20. And again, you can make it happen. Go higher, higher, higher. I'm going to go 50,000 samples. This is the idea of sampling distribution. Repeated samples of the same size over and over and over. So I've taken 50,000 samples. I know 50,001, that was my first one. Look at the distribution is normal. The mean is almost that. 999.99, right? 98, that's very close. And deviation of 20. So this is what central limit theorem tells us essentially. So hopefully I was able to help you understand central limit theorem a little better.